the point A is continuous at A. Okay, so let's do the proof. Okay, so the proof. Okay, so I suppose let's assume that the function is differentiable. So let's assume, okay, that f is differentiable. Okay, differentiable. Okay, and then let's show, okay, let's show that what we need to show is that it's continuous. So what we effectively need to show is that the limit of f of x minus f of a actually equals 0. Okay, so we need to show that the limit of uh, f of x as x tends to a, okay, minus f of a, okay, equals 0. So we need to show this, okay, but let's just actually consider this, yeah, okay. So so let's say, so the limit of f of x as x tends to a minus f of a, because this is what we need to evaluate. We need to evaluate this and show that's equal to 0, is actually equal to, we know that we can change the limit of f of x as x tends to a, that from this particular identity that these two things are the same. See, if this limit exists, okay, well then what we're actually going to get here is when this evaluates true, we're actually going to end up with when this evaluates, when h tends to 0 here, what we're going to end up with is f of a, if that makes sense. So actually this is the same as, this piece here is the same as the limit of f of a plus h as h tends to 0. Okay, so this is tightly coupled to the limit, minus f of a. Okay, now f of a is actually just a value. Okay, it's just a number. It's the function f evaluated at a. So what we can do is we can bring that back into the limit. So this effectively is equal to, let me bring this over here, this is equal to the limit of f of a plus h minus f of a, okay, as h tends to 0. It's equal, this is the same as this here. The limit now is being evaluated. Don't forget we have a theorem, or we have an identity that says the limit of a plus b is the same as the limit of a plus the limit of b when both of them actually exist. So what we're doing is we're bringing these two things back in together here. So what this becomes now is, now what we really need to get is we need to try to extract out of here this differentiable function. Now, what does it mean to be differentiable? It means that f of a plus h minus f of a all over h exists. So we're nearly there here. All that we're missing is dividing by h. So this becomes the limit of f of a plus h minus f of a. Well, let's actually just divide it by h, okay, as h tends to 0, okay. So this isn't the same as this because this has been divided by h. But what we can actually do is we can actually multiply this by h. Yeah. So you can see that the two h's. So we're actually introducing h over h here. Okay. So now what we have is we have a product. So once again, this is this here. We have the limit of a times b is the same as the limit of a times the limit of b. So this becomes now the limit of f of a plus h minus f of a all over h as h tends to 0 times the limit of h as h tends to 0. But hang on a moment here. What we can actually see is that this particular thing here, well, what is it? It's the definition of differentiability, okay? And we've already assumed it's a definition of differentiability, okay? A function f is differentiable at a point A if this particular limit exists. Now, what we started this proof off with is that we assumed that f is differentiable. So assuming it's differentiable means that this limit exists. And we've said, let's call it, okay? So as h tends to 0, the zeros are gone. This actually becomes f of a, so, or f prime of a. So what we're going to call it is f prime of a. So this actually now becomes equal to, this piece here is f prime of a. But hang on a moment, the limit of h as h tends to 0 is simply 0. So this is times 0, which equals 0. So what we've just shown here is this fact, okay, so we've just shown that this thing here, okay, equals 0, which is our definition of continuity. A function f is continuous at a point A if its limit, okay, uh, as x tends to a is equal to it evaluated at the point a itself. Okay, and that's what we've actually shown. You can see here we have to show this, okay, which effectively is that we just show that the difference between them is equal to 0. So we started off with the difference between them. Okay, we assume that it's differentiable. So we started off with the difference between them. So we try to force this thing into what it means to be a differentiable function by introducing h over h, which ended up giving us this thing here, which is the concept, is the definition of differentiability. Okay. But the fact that the limit of h as h tends to 0 is 0, okay, results in that this product actually is effectively equal to 0. Okay? The important thing here is that this exists. Okay, we've assumed it to exist. Okay, so this exists. This is 0. So what we end up with is something that exists times 0 is actually equal to 0. Okay, guys. Once again, this was Jonathan Lambert with Maths and Stats. And I hope that this video was in some way intuitive. And more importantly, I hope that was helpful for you. And thanks for watching. Okay, bye-bye.